Welcome back to today's session. We're thrilled to have you join us again as we continue our journey through the history of AI, inspired by the book The Fourth Industrial Revolution and 100 Years of AI, 1950 to 2050 by Dr. Alok Aggarwal. Last time, we took a deep dive into the early days of AI, starting from the 1950s and taking us through the 1970s. We explored how AI was born, the rise of machine learning, and how breakthroughs like single and multi-layer perceptrons started to shape what we know today as AI.
We also talked about the initial boom phase, the commercialization of AI, and unfortunately the first AI winter, the period when AI faced a major setback.
But today, we're picking up right where we left off. We'll explore the second AI winter and the resurgence of AI between 1980 and 2010. We'll look at the hype and bust around expert systems, dive into the reasons for the substantial growth of AI systems during this time, and take a close look at the emergence of support vector machines, a key development in AI's evolution. So stay tuned, because this is where things really start to heat up again.
So let's start with expert systems. They have a story that's full of twists and turns, almost like a Hollywood drama.
I'm intrigued, but before we get too far, let's unpack this a bit. For those who might not be familiar, what exactly is an expert system?
Well, imagine if you could capture the knowledge of a top expert in a very specific field, like a doctor, and then you translate all that expertise into a computer program. That's essentially what expert systems aim to do.
Okay, so they're like digital versions of those really smart people we all wish we could call up when we need an answer.
Exactly. They use a knowledge base, which is like a huge library of facts and rules. Then an inference engine acts like a detective, applying logic to solve problems and answer questions.
So instead of learning from data like machine learning, expert systems rely on pre-programmed knowledge, right? But where did this all start?
The origin story. It all began in the 1960s with a program called Dendril developed at Stanford. It could analyze mass spectra data and identify unknown organic molecules, pretty groundbreaking for its time. And, by the 70s and 80s, expert systems were everywhere, helping with medical diagnoses, geological discoveries, and more. It was a boom time for expert systems.
It sounds like they were poised to take over the world.
Yeah, but then there were challenges. A major hurdle was knowledge acquisition. Trying to capture all that human expertise and convert it into computer code was incredibly difficult and time-consuming.
So, it was like trying to download decades of experience into a machine?
Exactly. As systems got more complex, managing these knowledge bases became a logistical nightmare, time-consuming and expensive. Plus, with the rise of cheaper and faster computers in the late 80s, the specialized machines needed for expert systems became obsolete.
So that shift led to the decline of expert systems?
Yeah, and AI pioneers like John McCarthy and Marvin Minsky, who'd lived through the first AI boom and bust, warned about the inflated hype and predicted another AI winter.
Wow, they really saw it coming.
Yeah, but sadly, between 1987 and 1993, AI funding dried up and progress slowed. Even big projects like Japan's fifth-generation computer project, aimed at creating intelligent systems, were abandoned. A real tough time for AI.
But expert systems didn't disappear, right?
No, surprisingly, they made a comeback in the 2000s, mainly thanks to their integration into knowledge graphs and the semantic web.
Knowledge graphs? Aren't those used a lot today?
Exactly. They're like massive networks of interconnected data points that help organize information. Think of them as giant mind maps linking entities like people, places, and concepts.
So they help structure data in a way computers can understand. But where do expert systems come in?
Remember those inference engines? They're now applied to knowledge graphs, allowing us to extract insights and make predictions far beyond traditional data analysis.
So expert systems boosted by knowledge graphs are making much smarter decisions now.
Exactly. And this resurgence is happening across industries like healthcare, where they help diagnose diseases, recommend treatments, and predict outcomes.
Wow, so expert systems are really shaping personalized medicine now. That's incredible.
Absolutely. They're also helping banks detect fraud, assess risk, and even provide personalized financial advice. In e-commerce, they're driving recommendation engines that suggest products based on your browsing. The core idea of capturing human expertise and automating reasoning is still just as powerful, but they still face challenges today.
It's wild how far expert systems have come, from analyzing molecules to influencing healthcare and finance decisions.
Exactly. We've been trying to bottle up expert intuition for decades. But with all the advances in machine learning, could expert systems remain a specialized tool, or could they make a major comeback?
So could they work together with machine learning instead of competing?
Exactly. Machine learning can help automate the creation and updating of knowledge bases, while expert systems provide reasoning and transparency, something machine learning often lacks. It's like a super efficient librarian explaining why certain information is relevant.
I see. They complement each other's strengths. Can you give examples?
Sure, in medical diagnosis, machine learning analyzes scans, while the expert system cross-references symptoms and medical history to offer a nuanced diagnosis and treatment plan. In fraud detection, machine learning flags suspicious transactions, and expert systems dig deeper to uncover patterns.
It's more comprehensive, that's for sure.
It's exciting to think about, but we must ensure these systems are reliable and free of bias. Making sure they're trustworthy is key, especially when making life-altering decisions.
So, like with any powerful tool, it comes down to using it responsibly.
Exactly. As we move forward, we need to prioritize transparency. Make sure that these systems are understandable and accountable. The more we demystify them, the more we understand how they work, the decisions they make, the more trust we can build.
Makes sense.
Well, it was truly a fascinating conversation on expert systems.
And now, moving on to another really exciting topic, the AI boom.
Oh yeah, that incredible surge in AI development seemed to come out of nowhere between 1998 and 2010.
Exactly. It is fascinating to see how all the pieces came together, right? We often think about the algorithms, but AI wouldn't be where it is today without advancements in other areas too, like the hardware, the data, and even the way we develop software.
All right, so it was like a perfect storm of progress. Let's start with the famous Moore's Law. Computing power doubles roughly every 2 years. How did that impact AI?
Moore's Law wasn't just about making things cheaper and faster. It enabled researchers to finally test and refine AI algorithms on real-world data, unlocking new possibilities.
So it's like someone gave them a massive sandbox to play in?
Exactly. And as that sandbox grew, researchers could tackle increasingly complex problems. Some AI algorithms were so demanding that even with faster hardware, training models like neural networks with millions of images could take weeks on a single computer.
I see the issue. So, how did they get past that bottleneck?
That's where parallel and distributed computing came in. Instead of one computer doing all the work, they connected multiple machines to form a supercomputer, each handling a part of the problem at the same time, which drastically cut down processing time.
Like a team of experts each working on a piece of a giant jigsaw puzzle.
Exactly, and a big leap came in 2004 when Google introduced MapReduce, a programming model that let researchers process huge datasets across multiple computers. A real game changer. And then in 2006, Hadoop came along as an open-source alternative, making this tech more accessible worldwide.
So we had more power and the ability to spread out tasks, but how did they speed things up?
That's where GPUs come into play. Originally designed for gaming, GPUs can perform many calculations in parallel, which is perfect for AI's heavy number-crunching needs.
So it's like a team of super-fast calculators all working together.
Exactly. A key 2006 research paper showed that convolutional neural networks, CNNs, ran 4 times faster on GPUs than traditional CPUs, which was a huge breakthrough.
That's a massive difference.
It really was, and it kick-started the widespread use of GPUs in AI.
So the hardware was set, but even with all that power, AI still needed something to work with, right?
Right? Algorithms are like master chefs. They need a ton of quality data to create something amazing. And that's where the big data explosion came in. We're talking about the huge amounts of data being generated every minute from social media, sensors, online transactions, you name it.
It's crazy to think about how much data is out there.
Exactly. And all this data became the perfect training ground for a new generation of data-hungry AI algorithms, especially in deep learning. The more data they have, the better they get at recognizing patterns and making predictions.
So the digital world basically became a buffet for AI.
Yep, key moments in this explosion included the coining of the term big data in 1997 and the launch of databases like NIST's handwritten digits dataset, followed by ImageNet in 2009, which became crucial for training image recognition models.
And social media platforms like Facebook and YouTube just fueled the fire, right?
Absolutely. The rise of social media, along with the proliferation of electronic devices, created a tsunami of data. Plus, open databases and crowdsourcing allowed people worldwide to contribute to data cleaning and labeling. But even with all this data, how did this technology become accessible to researchers? It couldn't all be locked away in expensive labs.
So, how did they get access?
The open source software movement played a huge role. Open source software allows anyone to use, modify, and share code freely. In AI, this started with Torch in 2002, followed by frameworks like Theano, TensorFlow, and scikit-learn. By 2010, there were over 50 open source AI frameworks available.
Wow, so researchers everywhere suddenly had access to powerful tools.
Exactly. This spirit of openness accelerated AI development and adoption.
It's amazing how all these elements, Moore's law, parallel computing, GPUs, big data, and open source software, came together at just the right time.
It really shows how interconnected innovation is. A breakthrough in one field can ripple across others, driving progress in unexpected ways.
And of course, we can't forget the role of data.
Absolutely. Data was the fuel these AI algorithms needed to learn and evolve. Without it, even the best algorithms would just be theoretical.
Exactly. Without those massive data sets, AI would have never reached the level we see today.
Exactly. So have you ever wondered how your phone recognizes your face, or how Netflix seems to know exactly what you want to watch next?
That's what we're going to discuss next, how computers actually learn to do that, specifically using a technique called support vector machines.
So, how can computers, which usually rely on logic and straight lines, make sense of all that messy real-world data?
That's what mathematicians refer to as nonlinear data.
And when we're talking about the straight line stuff, that's all about linear algebra, right?
Exactly.
So how do we get computers to handle all that nonlinear complexity?
Well, that's where support vector machines, or SVMs, come in. Think of them as master code breakers. They can take those messy, real-world problems and transform them into something a computer can actually work with. Kind of like translating between two totally different languages.
Okay, I'm starting to get the picture. But before we dive deeper into SVMs, can we take a step back and talk about machine learning in a way that even I can understand?
All right, imagine you're trying to teach a computer to tell the difference between pictures of cats and dogs. Instead of giving it a list of rules like cats have pointy ears and dogs have floppy ears.
Because there are always exceptions, like my aunt's chihuahua with the pointiest ears ever.
Exactly. So instead of rigid rules, you show the computer tons of pictures labeled either cat or dog.
Like thousands of pictures?
Maybe even millions. And the computer uses algorithms to analyze all these images.
Algorithms?
Just a fancy term for a set of instructions. The computer learns patterns from the data and figures out its own way to tell a cat from a dog.
So it's like the computer is creating its own rules based on what it's learned. That's pretty cool.
Exactly. And that's where SVMs shine. They're one of the most powerful tools for this type of learning.
So how do they work? What's the secret sauce that makes SVMs so effective?
Let's use a simple example. Imagine a bunch of gray and black dots mixed up on a piece of paper. Our goal is to separate the gray dots from the black dots. Now, if the dots are scattered randomly, we could probably just draw a straight line to divide them, right? But what if those dots are arranged in a circle?
A circle?
Yeah, with all the gray dots inside the circle and all the black dots outside.
A straight line wouldn't work for that.
Nope. You'd need a curve to separate them accurately, like a circle. And that's where SVMs come in.
They can handle those more complex scenarios.
Right? Where a simple line just won't cut it.
Okay, so how do they do that?
Well, they use a pretty cool trick. They map the data into a higher dimension. It's like taking those docs on a flat piece of paper and popping them into 3D space.
Wait, hold on. They add another dimension?
It sounds crazy, but it works. Think about it this way. In 3D, you have more room to move around. you can use a flat plane to cut through that 3D space. And that plane can separate the gray dots from the black dots, even though they were all mixed up in that 2D circle. And that's why SVMs are so powerful.
They can see patterns in higher dimensions that we can't even imagine. For example, in medical diagnoses, an SVM can analyze tons of data about your health, like blood pressure, heart rate, and it can see connections that a human doctor might miss, leading to better diagnosis and better treatment.
That's incredible.
And we use SVMs for all sorts of things. They're quietly working behind the scenes, making our lives easier.
Exactly. And as we generate more and more data, SVMs are going to become even more important.
This is blowing my mind, but I have to ask, are there any downsides to this technology?
Well, now, technology's perfect. One of the challenges with SVMs is they can be computationally intensive when you're dealing with massive data sets.
So it takes a lot of time and energy to run these things.
They can. And another thing to keep in mind is that SVMs are sensitive to the quality of the data. So if the data is bad, the results will be bad too.
Even the smartest algorithm is only as good as the data it's given.
Couldn't have said it better myself.
So, why should the average person care about SVMs?
Great question. SVMs are already impacting our daily lives in significant ways. They're behind a lot of the tech we use every day. And as computing power grows, almost exponentially, SVMs are becoming even more critical in solving complex problems and driving innovation.
So it's not just about how computers learn, but how that knowledge can improve our lives.
Absolutely. It's about making our lives safer, more efficient, and even more personalized. Who knows what exciting applications we'll see in the future?
Wow, that's mind-blowing. But before we get lost in possibilities, let's recap what we've covered about SVMs.
Sure. It's funny when you realize that SVMs are already saving us tons of time every day by keeping our inboxes clean. They can recognize spammy emails so you don't have to deal with them.
And they're even used in predicting the stock market?
Exactly. Financial forecasting is another area where SVMs are making a big impact.
Imagine being able to predict market trends. That's valuable information.
Definitely. And the possibilities are endless. SVMs excel at classification, so they can be applied to everything from image recognition to medical diagnoses.
Even personalized advertising?
Yes. Ever notice how ads seem to follow you around after you look at something online? That's SVMs analyzing your browsing and purchase history to show you relevant ads.
So, SVMs are like this hidden engine powering so much of the tech we rely on.
Exactly. And as we generate more data every second, SVMs become even more powerful in refining their predictions.
This is incredible. I'm starting to see SVMs everywhere now. Okay, so with all that said, why should we care about support vector machines? I mean, this is all fascinating, but how does it actually affect our lives?
Well, I think the key takeaway here is that SVMs are already shaping our world in profound ways. Even if we don't realize it, they're behind so many of the technologies we use every day, and they are going to play an even bigger role in solving complex problems.
So it's not just about understanding how computers learn.
It's about understanding how that knowledge can be used to make our lives better, safer, and more efficient.
And who knows what amazing applications we'll see in the future.
The possibilities are mind-boggling. Well, I think this is a good point to stop and recap what we've learned today. So, we started by talking about the second AI winter and the resurgence of AI between 1980 and 2010. We touched upon the hype and bust around expert systems and discussed the reasons for the substantial growth of AI systems during this time.
We also took a closer look at the emergence of support vector machines, which become a key development in AI's evolution. And then we spoke about the AI boom. The incredible surge in AI development seemed to come out of nowhere between 1998 and 2010.
Then we started talking about machine learning and how computers are learning to think more like us. And then we really dove into support vector machines, these amazing mathematical tools that can find patterns and all sorts of data.
And we even talked about how they do that by using higher demand information. And then we saw how SVMs are being used in so many different areas like spam filters, medical diagnoses, and even financial forecasting.
Absolutely. SVMs are far more than just a mathematical concept. They're powerful tools, solving real-world problems that impact all of us. And as we continue to explore their potential, we can look forward to a future where technology improves our lives in ways we haven't even imagined.
Exactly. So guys, stay tuned for our next episode, where we'll dive into the revival and expansion of deep learning networks and the exciting progress being made in their commercial applications. Until then, keep those brains buzzing and happy learning.